Hello everyone. Today we are going to start module 2 concepts of remote sensing with lecture 4, that is optical remote sensing. So we will start this lecture with optical remote sensing. In this lecture let us start with the panchromatic, multispectral and hyperspectral. So I hope you remember this graph. So here it shows that what are the different bands which is measured by Landsat satellites, right? The band means the images. So here we can see the first, second, third, fourth, fifth and seventh band of Landsat ETM plus that is captured in these wavelength ranges, right? And I also explained you in the previous lectures, let's say this is 400 to 700 nanometer, right? And if I design a satellite or sensor which can capture one image using this wavelength range, one image can be generated using this wavelength range and another can be using a broad wavelength range, right. So, this is up to the developer of this sensor, what is the objective of the mission, and then accordingly we select what are the wavelength ranges that we have to use to design a particular sensor. So, in this particular sensor there will be 3 different types of detector, one which is sensitive between this to this wavelength, another set of detector which is sensitive between this to this, another detector which is sensitive between this particular wavelength range. So, in this scenario this particular sensor, let us say it is X sensor, right, which is capable of generating 3 bands. 3 bands means these are 3 images, right, and these images have different wavelength ranges that is being used here, right. So, I hope this is clear, and then we also learned that what is the relationship between the wavelength and energy. As we are towards the shorter wavelength, we have high energy. As we are moving towards longer wavelength range, we have low energy. So, if an image is generated in this particular wavelength, right. So, here we have high energy. Here when we are moving to second image, it will be comparatively less. Here when we are moving further in the longer wavelength, here we will have further less energy compared to this, right. So, the pixel which is generated by this image, the pixel which is generated by this particular sensor or the detector, this spatial resolution will be fine resolution compared to this and compared to this. Then again if I compare this spatial resolution with this, here this will be more finer than this one because we have more energy in the shorter wavelength range. So, taking these things into the concept, considering these basic information, we can design a particular sensor which is sensitive maybe in the whole wavelength range starting from 400 to 700 nanometer or maybe 1500 nanometer, right. So, if I generate a single image using this whole wavelength range, so this is a broad wavelength range. So, if we are using the broad wavelength range, energy is very high here. So, if we have energy high, then our image or the detector which is looking at a particular area, right, can identify very small energy which is released by this particular pixel because energy is high. So, the energy will be sufficient to travel through our atmosphere to space and getting captured by this particular detector. When we are moving towards longer wavelength range, what we do? We try to increase the size of the pixel so that energy will be sufficient to be captured by our sensor, right. So, here when we are using this whole wavelength range, we have good amount of energy to be resolved by our sensor. So, our pixel size will be in the order of maybe centimeter, right, or millimeter or meter, right. So, here this kind of setting is known as the panchromatic image. If we generate an image using a broadband spectral range and the spatial resolution of this particular image is high, and if the spatial resolution is high, we will have more feature details in this particular image, right. So, this is called panchromatic, and remember one thing, that when we are talking about the panchromatic images, these images are single band image. It does not have multiples of bands or multiples of images captured in the same wavelength, right. So, here this is single band image which has high spatial resolution or fine spatial resolution, and it will have more object information. When we talk about multispectral remote sensing, so here this is the example of multispectral. Here the first criteria is number of bands should be more than 3 or equal to 3. So, minimum is 3 bands. And then another thing is, referring to this particular plot, you can see here that these spectral ranges are different and they are having gaps in between, right. If you see this, here you have gap, here you have gap, right. That means the gap is where we have not generated any image, or there is no specific sensor which is capturing this particular wavelength information, right. So, we have 1, 2, 3, 4, 5 and 6 number of images. So, we have 1, 2, 3, 4, 5 and 6. Now, when we have 6 images, that means the same area is captured by 6 different sets of detector sensitive in different wavelength ranges. So, these 6 images will have different information related to your surface or the object. So, if we consider first pixel of first image which is capturing the same area located in the first pixel of second image. Likewise, third image first pixel of fourth image, first pixel of fifth image, first pixel of sixth image, they are basically representing the same area on the ground. So, if we consider this first pixel here, right, of all these bands, that means we will have 6 different values captured in 6 different wavelengths. Remember these wavelengths, right. So, if we try to plot this information, so here you have wavelength and here you have, let us say, reflectance for example. Now, the first information goes here, which is here maybe, second it goes maybe here, third it will go here, fourth will go here, fifth will go here and sixth is going here. So, once we have this, then we can have this kind of plot which is representing the characteristic of the material or the object or whatever area which is captured within this field of view, 1 pixel size. So, the 1 pixel size is, let us say, if it is 25 by 25 centimeter or let us say 1 meter by 1 meter. So, this particular graph is representing the behavior of material which is present in this field of view, means this whole pixel behavior, right. So, smaller the pixel, you will have more separation in the object, that it is clear from the panchromatic image, right. So, this is the multispectral, where the number of bands should be minimum 3 or more, and there may be a possibility that there will be a gap between the first image and the second image, or the third image and the fourth image. So, these gaps are allowed in multispectral, right. So, this is called multispectral remote sensing data, right. So, now I will show you one curve which can be referred to understand this particular concept. Here the same plot, it is first value coming here, second value here, third value here, fourth value here, fifth here and sixth here, right, and then it is connected with these straight lines. So, once we refer this, we can identify the material, whether it is X material or Y material or Z material, right. Now, if you refer to the basics of remote sensing, where we say that materials chemical composition and internal atomic structures are responsible for this kind of spectral plot, where if let us say this is one of the plot. So, this characteristic absorption position, let us say this is lambda 1 and this is reflectance, right, and this is material X. So, if this is reflectance, which is a unique property, remember. So, if this material is giving you one characteristic absorption feature at lambda 1, that means X can be identified using the lambda 1. Now, similarly for Y, there may be a possibility that it has two absorption feature in this particular wavelength range. So, if I have to identify Y, then I have to look for these two, because material can give you one single characteristic absorption feature or a set of characteristic absorption feature, and based on that we identify. Now, referring to this multispectral setting, now do you see that between this point and this point all the informations are present? No. Why? Because within this wavelength range we do not have any image, right. Since we do not have any observation in this particular wavelength range, we are missing this information. Maybe it is supposed to be like this, which is missing in this particular multispectral data. But when we have a different types of measurement, where we are having the contiguous measurement, right. There is no gap between the first and the second image, right. So, we will have this kind of measurement, and the number of band is minimum 10, and the wavelength difference between the starting and end of this particular image, that is the bandwidth. So, that should be in the order of 10 to 20 nanometer, right. So, this 10 to 20 nanometer minimum number of band should be 10, right, and this is contiguous. So, this is contiguous, right. So, this is contiguous means there is no gap between the first and second, and here earlier we had these gaps, right, remember. So, once we have this kind of setting, and when we generate such images, once we have this kind of measurement where the number of band is more than 10 and the band width is in the order of 10 and 20 nanometer, right, and it is contiguous in nature, we call it hyperspectral remote sensing data. And you see the spectral behavior gets changed because you have so many measurement here, right. So, once you have this kind of measurement, it gives you more information about the material characteristic, what is its chemical composition, what is the internal atomic structure, and then you can more precisely identify the material. So, when you are going with the hyperspectral remote sensing, you can identify what kind of mineral, what kind of rocks are present in the pixel area, or what kind of vegetation species, what are the different types of water, whether it is mixed with suspended sediment. Such information can be easily identified with hyperspectral remote sensing. So, we start with panchromatic, then we move to multispectral, and then we also understood the hyperspectral concepts. Now, this particular slide will give you more information about the broadband, multispectral, hyperspectral and ultraspectral remote sensing. So, when we talk about this broadband, so here you can see there is only one image which is generated using this particular wavelength range, right. So, once we have that, that means we have enough spectral range and the energy will be very, very high. Whereas, this multispectral, this will have both, right. In multispectral, the same wavelength range is used to capture different images, right. So, here you can see so many images were generated, and in between we also have few gaps. So, as per the definition, if we go, minimum number of bands should be 3 and in between gaps are allowed, right. So, this is continuous measurement where in between wavelengths are not used to generate the images. Now, when we move to hyperspectral, here we have hundreds of band, right, and this is contiguous in nature. There is no gap between the first image and the second image and the third image, fourth and so on, right. So, here you will have very good spectral resolution. If we have this ultraspectral, this ultraspectral is a concept where we have thousands of band and the bandwidth will be further low, right. So, the bandwidth, the starting here it can be in the order of let us say 410 and then 420, 430. So, these 3 images are generated at 410, at 420, at 430. But here if we see, it is much finer, right. So, here you will have in the order of few nanometers, right. Here it is 10 to 20. Here it is a comparatively broader wavelength, right. Here it is a broad band which is using a very long wavelength range to generate one image. Here you have minimum 3 image, here you have tens or hundreds of images, here you have thousands of images, right. So, that is the difference between panchromatic, multispectral, hyperspectral and ultraspectral. I hope this concept is clear to you. Now, we will see the advantages of hyperspectral remote sensing, multispectral remote sensing and panchromatic images, because we have different application and for different application different types of data products are needed, right. So, starting from this panchromatic, what we do is we identify the object, activities and events. That is the prime objective of our panchromatic image. Now, once we are moving towards this multispectral, so here we have only one image. So, here one pixel will give you one value, but when we are moving to multispectral, here you have multiples of images or bands. That means, for single pixel you have multiples of values that can be used to identify the material. So, when we are moving from here to here, our spectral resolution is increasing, and once we are moving towards hyperspectral, we are having further high spectral resolution. So, once we are moving towards this multispectral data, then we go for the qualitative study, the identification and discrimination is very easy, because we have a spectral profile, right. So, but here it will be with few points. Now, once we have this multispectral, we try to see the hyperspectral, what advantages we will have. So, in hyperspectral we will have qualitative and quantitative study, and which can be used for the abundance estimation, characterization of the material and discrimination of the target. It is very easy with the hyperspectral data when we compare with multispectral and panchromatic. And remember, remote sensing image analysis will give you the information about the object characteristic, and that is quick and non-destructive in nature. Here, because we are not changing the form of the target, we are just trying to gather the information which is coming from the source, and based on the behavior of the light in different wavelength, we try to analyze them and we try to find what material it could be, right, whether it is X or Y. Now, this particular slide is just refreshing the concept of atmospheric window. I hope you remember the atmospheric window. Here we discussed what is the atmospheric transmission and how the different wavelengths are behaving in our atmosphere, right. So, in the atmosphere there are few wavelengths which are completely or partially blocked, some of the energies which are allowed by our atmosphere. So, this information can be used by the sensor developer, that which particular wavelength we should use to develop a sensor and what could be our possible applications, right. So, here you see in the visible range you have 400 to 700 nanometer, in this infrared which is 0.7 to 3 micrometer, then thermal infrared, and here you have all these atmospheric constituents which is interacting with the incoming radiation, and the resultant is reaching to our surface and then it is getting reflected, right. So, I hope you remember this, and based on this we try to see what kind of remote sensing we can do possibly from the space. I hope you remember the reflective domain. So, where we use this 400 to 2500 nanometer for measurement of the reflected energy, and here you see from 2.5 to 14 micrometer, that is being used to measure the emitted energy, right. So, here this particular wavelength range is very important when we talk about the thermal remote sensing. Thermal remote sensing, and most of the space borne thermal sensors are active in this particular region, you see, right. So, in this region. So, in the previous lecture I have already covered the part of optical remote sensing. So, the reflective domain which is 0.4 to 2.5 micrometer, and then I also explained you the DN, radiance and reflectance, why reflectance is a unique property and how we can utilize this information to identify the material or to generate the information about the target, right. Now, here this particular slide explains thermal remote sensing also have the impact of atmospheric emissions, right. Since we are talking about this thermal wavelength which is 2.5 micrometer to 16 micrometer, and in this region what we measure? We measure the emitted information or emitted energy by the target, and this particular wavelength we will be seeing in detail how we can utilize to extract the information. So, the wavelength range for the thermal remote sensing is from 3 to 16 micrometer. However, I told you that 400 to 2500 nanometer is the reflective domain. Now, 2.5 to 3 micrometer, what is happening there? So, basically what happens, this is the wavelength range where we have the more atmospheric involvement, and then this 2.5 to 3 micrometer, that is the overlapping region of reflective and thermal remote sensing. So, it is very difficult to segregate these two information. So, we try to avoid this 2.5 to 3 micrometer, and in thermal remote sensing we use only 3 to 16 micrometer wavelength range. Temperature or emitted energies are measured through thermal remote sensing. It provides different information than the reflective domain. This is 0.4 to 2.5 micrometer. Now, in the 400 to 2500 nanometer, what happened? The sun is illuminating this particular target, and then it is getting reflected and it is getting measured by our sensor. So, this is giving you the superficial information, right, because the depth of penetration of 400 to 2500 nanometer is as good as their wavelength. It can be considered as a thumb rule that depth of penetration of any energy is equal to their wavelength. So, if you see here, this is giving you the superficial information, this 400 to 2500 nanometer, right. And when we talk about this thermal remote sensing, where the wavelength is 3 to 16 micrometer, the depth of penetration will be 3 to 16 micrometer, but no, you can't apply the same logic here, because what happens when the object receives the energy, some amount of energy is getting absorbed. Once it is absorbing the energy, it is going to its volume, right. Because of the volume, it will absorb the different amount of energy, and to maintain the equilibrium with this surrounding, extra energy will be released at the longer wavelength region. So, this longer wavelength region is nothing but the 3 to 16 micrometer. Now, this emitted energy is not because of the surface, right, it is because of the volume of this particular target. So, if the volume is different amount of energy will be absorbed, right. So, that is what it provides, different information. So, different information means it is providing you the volumetric information, right. It provides the volumetric information. Hidden and subsurface objects can be identified. So, since it is coming from the volume, right, remember it is because of the volume. So, this volume can give you the information about what is hidden here. If there is a metallic body or non-metallic body, that you can easily identify with the thermal remote sensing. So, we will see some of the examples in the coming slides, but one thing which is very clear from this basic principles, that if you use thermal remote sensing, you can identify the hidden or subsurface objects. So, one prime application could be the identifying the landmines, right. That is very much possible with the thermal remote sensing data. Now, the application, the industrial maintenance, pipeline failure zone or underground leaks, that can be easily identified using thermal remote sensing. You can see here that this particular section of the pipe is having different information about the temperature. So, there could be a leakage, right. Here you can see this underground pipe is leaking, and because of that this particular area is having different thermal property, right. Here this is one way of mapping the underground pipeline, that which of the section is leaking and how to identify where to go and fix them. So, this is very relevant information when we go for the transportation of petroleum from one place to another place using the underground pipes. The habitat monitoring, you can see here, in the night you will have the vision, right. So, during the daytime it is very hard to identify or segregate them from the background. Thermal remote sensing is very useful when we go for the corridor analysis. So, the corridor analysis will give you how many animals are traveling in the night and which path they are using. So, that can be used here, right. In the forest fire also, this thermal remote sensing can help, and it can give you the information to restrict the spreading of the forest fire, and this is one of the best application of the thermal remote sensing. Here you can see this particular image, which is very interesting. Can you see anything here in this particular area? This image is generated using normal camera, right. But when we have the thermal camera here, you can easily find that one person is basically hiding here, right. This kind of advantages we will have when we are moving from reflective domain to thermal domain. So, once again we will see the basics. Thermal remote sensing wavelength is between 3 to 16 micrometer. So, the commonly used wavelength by the satellite is 8 to 14 micrometer. Through thermal remote sensing, infrared radiation emitted from the earth's surface is measured, right, and widely used for the earth's land and sea surface temperature. The other application you have already seen. Forest fire monitoring is one of the most important applications of thermal remote sensing. Now, we will try to understand why actually a particular material emits, right. So, object above 0 degree Kelvin temperature emits radiation, any object, right. The energy of particles of molecules in random motion is referred to as kinetic, internal, real or true heat, right. It can be measured through a thermometer. We all know that the temperature measured will be kinetic temperature. So, what we are measuring? We are measuring the kinetic temperature. The internal kinetic energy heat may also convert it to radiant energy. So, finally, when we measure the energy through thermal remote sensing is the radiant energy, right. This is external or apparent energy. Thermal remote sensing is measuring this radiant energy. You might have heard about the black body. The black body is a material, this is a theoretical material which absorb all the energy which is falling on it, and it is getting stored here. So, and we also know that any body which is above 0 degree Kelvin, that will emit the energy to maintain the equilibrium with the surrounding. So, if it is absorbing 100%, that means it will also emit 100%. So, we can say it is the true absorber and true emitter. So, both are 100%, but no object in nature are true black body. This is a theoretical concept. A black body absorbs all incident electromagnetic radiation regardless of frequency or angle of incidence, and it is an ideal and diffused emitter. So, it will emit equally in all the direction, right. So, but the emitted energy will be 100%. So, that is the nature of the black body. Now, once we have that, then can we measure the emissivity of a particular target with respect to black body? So, emitting ability of any object with respect to a black body is referred to as emissivity. So, we have the target, this is target and this is black body, and here since we are measuring the radiant energy, right. So, both the material, the black body and the target should be at the same temperature, right. So, it may be 30 degree. Now, when we compare this emittance or the emitted energy from this particular target with respect to black body at the same temperature, it is called emissivity, right. So, emissivity is a factor that describes how efficiently an object radiates energy with respect to black body. Emissivity of grey body is always less than 1. Remember, in the reflectance also I told you that it ranges between 0 to 1, and emissivity is also ranging between 0 to 1. So, for a black body it will be always 1, right, because that is a true reflector and true absorber. So, this emissivity of black body will be 1, and this equation can be referred to calculate the emissivity of a target at a particular wavelength, and here we need these two information: radiant exitance of an object at temperature I, radiant exitance of a black body at temperature I. So, if we have these two, this value will be between 0 to 1, right. So, this can be also considered as a unique value to identify or characterize the material, right. So, this is also a unique value like your reflectance. You might have observed this in day to day life, that at midnight we have the lowest temperature, then morning again this will be reduced, and then slowly when sun rises, the material or the target, they start absorbing the energy, and then temperature will be high in the afternoon, and then slowly it will go down. So, this is called the diurnal cycle of any material. So, this is for the bare soil or rock, this is for water, right. So, here you can see one thing, that if we are changing the material, they are having different types of this diurnal cycle, right. So, why so? Because it also depends upon their thermal properties. So, if we consider bare or soil or rock, so whether the rock is metallic rock or it is non-metallic in nature, what kind of soil we have. So, in such situation what happens, we will have different cycle or different temperature changes, right. So, considering this particular concept, can we use this concept, because if you see for the rock we had this peak at let us say 5 p.m. For water it is around 9 p.m. right. So, this difference in the peak, that is called the delta T, right. So, this is delta T, temperature difference in the peak of two different material, right. But for the same material, if we have to consider this rock, so this is one position and this is the lowest point. So, let us say this is maybe 6 o'clock. So, if we have this, then we will have this delta T for the same material, right, here. So, how much temperature difference we have for the same material. So, here we will have different values, and then accordingly you can subtract it, and then you will get the delta T is equal to this much degree Celsius, right. So, we will be using this concept in the further slide to further exploit this thermal remote sensing in our application. So, the emissivity of very common materials, you can see the emissivity, the value ranges between 0 to 1, and it is also varying for different material. Clear water, wet snow, human skin, green vegetation, concrete, tar, wet soil, dry soil, wood, granite rock, glass, sheet iron, stainless steel, aluminum foil, gold, everything is having different emissivity. So, here you can see the emissivity of gold is 0.02 to 0.03, right. So, here this is very low. Once we have the low emissivity, that means it is not absorbing the energy, it is reflecting more. So, that kind of information you can derive from even the emissivity value. So, if you have to choose which of the material is a good reflector comparatively, definitely you will say gold, or if gold is, if you have to use this to design an experiment, then let us say gold is costly, then aluminum foil is the second option we have. So, the aluminum foil is also having very low emissivity, that means the high reflectance, right. So, the emissivity depends upon target parameter and sensor parameter that is listed here. This is one very good map which is generated by NASA. Here you can see that this particular slide is meant to give you the information about how we are using the thermal remote sensing to check the thermal anomaly or how the temperature is changing over the year, right. So, you can see here this is the year, right, and the minimum maximum is written here. So, how it is changing over the time, and remember this is the anomaly in degree Celsius. So, these colors are representing this anomaly and this value can be considered. Now, it is going high, that means change is in the order of 3 degrees Celsius, right, and it is base period is 1951 to 1980. This graph is the summary of the previous video, and here you can see that how temperature is changing since 1980. This is 2024. If you see the anomaly is coming around here, right. So, anomaly is not that much, right. So, anomaly, the change in the temperature over the past few years starting from 1980, it is approximately 1.5 degrees Celsius, right. This is another video which is available from this particular website which is from NASA. So, here you can see how the temperature is changing since 1880 and it is going up to 2024. Here is the scale, right. So, again you will find the temperature difference or the anomaly in the temperature over the past 30-40 years is in the range of 2 degree or 2.5 degree or 3 degrees Fahrenheit. Here you see the temperature changes in the order of 2 degrees Celsius maximum, which says that the temperature has changed for our planet since 1980 and the anomaly is in the order of 2 degrees Celsius maximum. Like emissivity domain, you also have the atmospheric impact on the thermal remote sensing. So, here you can understand this, that emission is taking place here and the gases, aerosol, dust particle or the clouds, they are also interacting with the incoming radiation, and because of that you will have the atmospheric scattering or the absorption. So, you will have the atmospheric emission that is also getting along with your surface emission, that will give you the additional information which was not present at the surface, right. Atmospheric gases and suspended particles may absorb radiation emitted from the ground and subsequently emit their own radiation. Dust, carbon particles, smoke, water droplet can modify this thermal radiation by the emission in the atmosphere, right. So, this is very important to understand. Now, there is a concept of spectral emissivity. So, we have understood the concept of emissivity. So, this is the target, this is the black body and the temperature is, let us say, 30 degrees Celsius for both of them. Now, the light is falling on this target, the same light is falling on this black body and it is getting reflected. Some amount will be reflected here. If it is black body, it is 0, right, and the target is absorbing and then further it will emit the radiant energy. So, this radiant energy will be measured and this radiant energy will be measured from the black body at the same temperature. Now, like reflection, here also we will take care of the wavelength. So, let us say I have generated 3 images between this 3 to 16 micrometer, right, 3 to 16 micrometer. Now, the first pixel of this image, let us say this is here, this is here, this is here. All of them are absorbing or generated using the radiant energy received by the sensor, right. So, the first pixel of all these images are representing the same area. So, here first pixel of all these images, then we can have this 3 to 16 micrometer wavelength plot and the first pixel emissivity will be calculated. So, here this wavelength lambda 1, lambda 2, lambda 3. So, here we will measure the black body radiation at lambda 1 and then for the target and then we will calculate the emissivity, it will come here, then second will come here, third will come here. So, this particular information is called the spectral emissivity. Emissivity is a property of the material, how much it emits with respect to black body at the same temperature, and when we consider different wavelengths to measure the radiant energy and calculate the emissivity, we call it spectral emissivity. I hope this is clear. Now, you can see the spectral emissivity. So, the L lambda minus dWr lambda divided by black body. So, this dWr is basically the reflection. So, surface emissivity, lambda is the wavelength, this L lambda is basically radiance of the sample, dWr is the downwelling radiance of the reference surface and this is black body radiation. So, this black body radiance will be used to measure the spectral emissivity and we will take care of this wavelength everywhere, right. So, if it is lambda 1, it has to be lambda 1 at all the places. Useful for thermal imaging instrument capable of generating several bands between 3 to 16 micrometer, right. So, now if you refer to hyperspectral remote sensing, so hyperspectral remote sensing is a concept which says that we have contiguous measurement and we have good number of spectral bands. So, maybe tens or hundreds of bands, right, and the bandwidth is narrow. So, the bandwidth here, since we are talking about the thermal remote sensing or the thermal wavelength range, the energy will be low. So, this bandwidth is not sufficient to generate a smaller pixel. So, what happens? We have to either increase the wavelength range or increase the pixel size, right. So, here it was in the order of 25 by 25 centimeter, and here if you refer to any of the satellite thermal data, you will find it is in the order of 90 by 90 meter. That is the reason behind this coarser spatial resolution. Now, once we have this limitation from the space, because the energy has to travel through our atmosphere to space to be captured, but if we have a field instrument which is capable of generating this narrow bandwidth images in the thermal wavelength range, we can have the hyperspectral data. So, we will have hyperspectral thermal remote sensing, right. Now, we will refer to Kirchhoff's law. Here it says the incident energy is equal to absorbed energy plus reflected energy and the transmitted energy. After dividing the equation with EI, incident energy, this is absorbance, reflectance or transmittance, right. So, according to Kirchhoff's law, spectral emissivity is equal to the spectral absorbance. Good absorbers are good emitter and good reflectors are poor emitter. That we have understood with the help of black body, right. So, black bodies are good absorber, so they are good emitter also, but the other material which is present on the surface of the earth, which we call grey material, right. So, the grey bodies are neither a good reflector nor a good absorber. So, our emissivity value will be always below 1 and the reflectance is also below 1, right. So, we are talking about the natural material or man-made material which is neither a black body nor a good reflector, right. According to Kirchhoff's law, if we have the reflectance, we can calculate the emissivity, or if we have emissivity, we can calculate the reflectance by assuming all other components are 0, right. So, the kinetic versus radiant temperature of 4 typical materials, the black body emissivity is 1, right, and vegetation it is 0.98, wet soil it is 0.95, dry soil it is 0.92. So, you can see the emissivity is significantly different for all these different material, and that can be used to identify the material property. Now, referring to the thermal properties of a material, you can consider thermal conductivity, the rate of heat transfer through a material in a steady state. The unit is watt per meter square per Kelvin. Thermal diffusivity measures the transient heat flow through a material. Specific heat capacity is the amount of heat required to raise the temperature of a given mass of material by 1 degree. Melting point, temperature at which it changes from solid to liquid at atmospheric pressure. And the thermal inertia, it measures the response of a material to change in temperature. So, this is very important, because now we are going to see one example how thermal inertia is used to identify different material present on the surface of our earth. So, thermal inertia is the resistance offered by a material to temperature change. Ti can be explained as this. So, here we are using the density, thermal conductivity and specific heat capacity, that will give you the thermal inertia. Now, the thermal conductivity, if you see for all these material, it is different, density is different, specific heat capacity is different. So, is the thermal inertia. Once we have this thermal inertia, can we use them as a unique information to identify the material? So, that we tried, and we use this thermal inertia mapping using the satellite images. So, this particular paper has used the ASTER data, field investigation and samples were collected, and the ASTER data were used to identify the delta T. This is the temperature difference, and there are two different approaches, lookup table and ATIM approach, and then we derived the thermal inertia map. At the same time, the field day night temperature measurement were carried out, laboratory data on the thermal inertia, mineralogy and geochemistry were carried out, and then we tried to correlate these two, that how thermal inertia is used. We have used these two information together to identify the potential zones of ore mineralization. So, in this particular work, thermal inertia is used, and the apparent thermal inertia is calculated using this equation 1 minus A divided by delta T. A is basically your albedo, this is the broadband reflectance, and the delta T, remember the ASTER data was used to measure the temperature difference. For terrestrial and planetary application, the temperature gradient across the thickness of the surface cannot be measured. Therefore, Ti is estimated by using the temperature differences of the surfaces measured at different phases of the diurnal heating and cooling cycle. Remember, refer to my previous slides where I explained you the diurnal heating and cooling. Right. Beyond 1 meter depth, the diurnal variation due to solar heating ceases. Hence, 1 meter depth is considered where solar heating related heat transfer is involved in the application. That means, the emitted energy which is coming from the surface is basically giving you the information about the 1 meter column. Right. So, as an input in thermal inertia, albedo offers important information on the absorbed energy. Visible band of satellite images are commonly used to estimate the albedo, and this particular equation is used with ASTER data to calculate the albedo. Remember, if you are changing the satellite, you have to remap the bands. Right. The above equation can be directly used with ASTER data. In case of other sensor data, band number should be converted according to their wavelength. For the temperature difference, daytime and nighttime thermal images acquired in the same wavelength region can be used. So, this is one of the example, daytime at 2:50 p.m. and nighttime at 9:50 p.m. You can see during the daytime thermal data, you have different information, at night time you have different information, and when you subtract them, you will get the delta T, right. So, using this particular concept, apparent thermal inertia was derived. So, there were two approaches that were used in this particular work. One is ATIM approach, another one is the lookup table approach. So, some of the application of thermal remote sensing is lithological and soil type mapping, structural mapping, soil moisture related studies, study of thermal characteristic of volcano, vegetation studies, identification of hot water spring, thermal plumes in water bodies, and very useful in forest fire and coal fire. So, with this I will end this lecture and will continue this course with next lecture. Thank you.